Hey everyone, I'm going to go through parts 3 and 4 in the slides with you today, starting with natural forces or gravitation. So this is a picture of when I went skydiving with Jack Black here in Hawaii. Fun experience, I would recommend it, but I would never do it again. So while I was falling through the air there after jumping out of a plane, I was experiencing two forces, force of gravitation and then also some air resistance to kind of slow me down a little bit. So gravitation is a natural force. A natural force is anything that causes an acceleration without contact. So what natural forces do is they generate a field around an object. So think of like a magnetic field or an electric field or a field of gravity. So if we're thinking about gravity, if you're placed inside of Earth's gravitational field, you're going to accelerate towards Earth. So we've talked about gravitational force a little bit already. If you're put into the gravitational field, you're going to accelerate downward. So gravitation is a negative force. It causes a negative acceleration. And it depends on two variables, mass and distance between two objects. So the largest object of mass near us is the Earth. So we're gravitationally attracted to the Earth, which means that the gravitational pulls between us and your Chromebook or you and your chair, those are very small forces of attraction, and they're negated by the gravitational force exerted by the Earth. So that's why you're not slowly moving towards, your couch. Okay, that's what that slide says there. So there's also a gravitational pull between the Earth and the Moon, and that's what creates tides on Earth. The name for the gravitational force that's exerted on any object on Earth or on any planet or moon is called weight. So in our normal everyday lives, we measure weight in pounds using a scale, but the metric way to measure weight is with newtons. Weight is a force, and it's a measure of how much gravity's pulling you towards Earth. So weight depends on two variables. It depends on your mass and the acceleration of gravity. So on Earth, we know that the acceleration of gravity is 9.8. It's a negative 9.8 technically. We're pulled downward toward the center of the Earth. Your mass is the amount of stuff, the amount of matter that makes you up. So mass is a variable that never changes. As long as you as a person doesn't change, you don't lose any limbs or gain a lot of pounds or lose a lot of pounds, your mass stays the same. G can change if you go somewhere else, if you go to Mars or if you go to the moon. Then G, the acceleration of gravity, changes, and therefore your weight would change. So if you go to the moon, your mass stays the same, but your weight decreases because there's less gravity on the moon. The moon is a smaller object than Earth. So weight is a force. It's measured in newtons, and technically your weight is negative. It's a negative value. That sounds a little silly to say that I weigh negative 150 pounds, but technically that's the correct way to say that in physics because my weight is a downward force. So keep that in mind. We're going to use weight as a negative value moving forward. All right, so this just reminds you that your mass does not change due to your location. There's a flipping physics video here. If you feel like you need some extra practice, you can go to these slides, click this video, and he will walk you through some example problems. All right, but here's some practice problems here too that we'll do together. So practice with the weight equation. If you have a 10 kilogram child standing on Earth and you need to calculate their weight, you use the formula W equals mg. So mass is 10, G is negative 9.8. So the weight of this child is negative 98 newtons. Okay, if you took that child and you brought them to the moon, mass wouldn't change, so your mass is still 10 kilograms times G on the moon, which is 1.6, negative 1.6. It's about a quarter of what Earth's gravity is. Okay, so 1.6 times 10 gives us a weight of negative 16 newtons. All right, lastly, I'm going to do this problem with you here. An astronaut who has a weight of 1,000 newtons on Earth is transported to the moon. What is his mass on the moon? So the trick with using the weight equation, W equals mg, is that you can't mix planets and moons. Okay, you can't take the weight on one planet and the gravity on another planet or moon to find mass. You have to keep W and G the same planet. So if weight is 1,000 newtons on Earth, sometimes I use subscripts to help me keep track of what planet I'm looking at here. Then I have to use G on the Earth to help me solve for his mass. Okay, G on the Earth is negative 9.8. Technically, his weight on Earth is negative. He's being pulled towards Earth downward. So if we solve for mass, we have to take W divided by G. So when you divide 1,000 by 9.8, your negatives cancel. You get 102 kilograms. So that's his mass on the Earth. And like we said before, mass doesn't change no matter where you go. So that's also his mass on the moon. That's your answer. All right, moving on to part 4, which is vertical motion. So the reason why we talked about weight with vertical motion is because weight is always present. It's always a force that's acting downward on an object. So when we look at things moving vertically up and down, we always have to take weight into consideration. So remember that W equals mg formula. We're going to be using that a lot. Let me get rid of this, erase it all, move on. So this guy, he's rappelling off a cliff. He has a force of weight that's trying to pull him down to Earth, but then he has some tension in that cord or rope that's acting against his weight. So tension is one example of an upward force that could resist weight. If you're looking at something sinking in water, like a treasure chest in an ocean, you have weight trying to pull it down to the bottom of the ocean, the weight of that chest, but then you have a buoyant force acting from the water upwards. And then here's our skydiver example again. So we have weight trying to pull this guy down, but the parachute is providing some air resistance working against weight. Okay, so notice how weight is the force that acts downward in every case. So if one of these forces is bigger, either the upward or the downward force, there's going to be an acceleration in that direction because there's a net force in that direction. So moving forward, we're just going to use tension as our example for all of these problems, but keep in mind that tension could be replaced with buoyant or air resistance, depending on the situation. All right, so if you're pulling up a box by a cord or a string, you're going to have tension acting in that cord upwards, and then the force pulling downward is going to be weight. If you have something that's not accelerating, that means that weight is going to be equal to the upward force. So in this case, a light bulb hanging by a wire, there'd be tension in that wire. And whatever the tension value is, it would be equal to the weight because this light bulb isn't moving. It's not accelerating in one direction. So your forces are balancing. However, if you have the object is accelerating, then you're going to have a larger force. Either weight or tension would be bigger. If your box is accelerating upward, tension is the force that's winning. It's the bigger force. If you have the box accelerating downward, then weight is going to be the bigger force. In either case, if you want to solve for the acceleration, you just use Newton's second law. So it's the same equation that we've been using this whole time, net force equals ma. To solve for the net force, you would subtract these two forces. They're working against each other. Okay, so tension minus weight gives us the net force. And then if you're going to solve for the acceleration, you just divide out the mass. Okay, so net force, tension minus weight, divided by mass gives us acceleration. We're going to do a couple practice problems. So we have a climber here rappelling. Get rid of this. From the cliff. It tells us that there's a force of tension in the rope of 800 newtons. So it always helps to draw a free body diagram for these problems. It should always be step one. So you can visualize the forces that are working on this climber. So tension is an upward force. I'm going to draw that in, 800 newtons up. The force that's pulling him down is his weight. And the problem doesn't tell us what the weight is. The problem only gives us his mass. So you have to use that formula that we just learned, W equals mg, to solve for weight. So 90 is the mass. Remember, kilograms is a measure of matter. It's a measure of mass. So 90 times 9.8 gives us 882 newtons is his weight. Okay, so 800 newtons pulling up, 882 newtons pulling down. So my net force is going to be negative 82 newtons. Okay, there's extra 82 newtons pulling downward. So he's going to be accelerating in the downward direction. So then I take Newton's second law, net force equals ma, divide out the mass to solve for A. So negative 82 divided by his mass of 90 gives us an acceleration of negative 0.9. Okay. The work is written out. I know my pen is kind of messy here, but the next slide shows you all that work. And I wish there was a way to erase all of this at once, but there's not, or I haven't figured it out yet. So there's a couple more practice problems. The next one I want to go over with you because something interesting happens in the next problem. So here we have a crane. I'm going to draw my free body diagram because I know that's the first step that I should always do. Crane lifts a 40 kilogram crate upward with a tension force. Tension always opposes weight of 392 newtons. And then what acceleration will the crate move with? So I know that there's the downward force always opposing tension. Again, they don't tell us the weight, they just tell us the mass. So we need to use that mass, multiply it by 9.8 to get our weight. So when you do that, when you take 40 times 9.8, you get a weight of 392. So when you have forces balanced, then you have no net force, which means you have no acceleration. So that doesn't mean that the crate is not moving. It just means that it's not accelerating. So it's moving with a constant velocity. So it could be moving up, it could be moving down, or it could be not moving at all. We don't know, we aren't given enough information to know that, but we do know that it's not accelerating. It's not speeding up or slowing down in any direction. Okay, and the last one is just like the first two. You would have to solve for the weight and then use Newton's second law to solve for the acceleration. So give it a try and then enter your answer on the Edpuzzle. See if you get it right. And then the last slide here is a couple videos about air resistance. We got a Mythbusters clip and then also a crazy skydive by Felix Baumgartner a few years ago. You're going to watch these videos in an assignment next week, so you don't have to worry about these yet. But if you're interested, you can go watch them early. All right, that's it for today.